This topic is a lot. We cover several things and they all tie together and they're all based off of the Lewis diagram. And so as we're going through this section, I'm going to cover a lot of topics, then we're going to do an example and go back and apply that information to each example. So when we draw a Lewis diagram, it is two-dimensional. And so we don't completely understand all of its characteristics based on its two-dimensional shape that we're drawing on paper, because in reality, things are three-dimensional. They have that X, Y, and Z axis available to them. They're not a flat substance. And so there are different ways that we describe that three-dimensional shape. One of them is what we call VSEPR, and that is an acronym for valence shell electron pair repulsion theory. And VSEPR just means that once we draw the Lewis structure, we look at the number of shared and unshared valence electrons. And what happens is, because electrons are all negative, they're going to have some repulsion. They're going to repel each other and orient as far apart as possible. And so because of that, we draw our Lewis diagram first, and then we base it off of how many shared and unshared pairs there are. So these are the 5 main shapes we're going to see. AP expects you to know these 5 and more. These 5 are the most common. The more is rarely tested, but we're going to focus more on the common ones. So the black molecules is representing your central atom. The white molecules or atoms are representing your peripheral, the outside. The purples representing bonds. Those could be double or triple or single. We don't know based on this picture. And then these weird things that look like emeralds, those are actually your cloud of unshared electrons. So those electrons are repelling because they are unshared. So let's go through and name what these are, and then we're going to look at a chart here in a minute that sort of simplifies all this down. So this first one that you see is going to be considered linear. It looks like a line. It's all straight and together. Another thing you're going to have to know is you're also going to have to know the angles that exist between these bonds. And so in this atom, we have our central atom. We have 2 shared substances. They could be the same element or different elements, but they are on either side of it. And this angle from here all the way around to here is going to be 180 degrees. This one here has 2 shared regions, just like this one, but their shared regions are being pushed down because of this unshared set of electrons. And so up here, they are pushing down on this bond. So this is 2 shared, and this actually should have another one of these green things up here on the top. And in this one, we have 2 shared and 2 unshared regions. This is what we call bent. Because of these unshared pairs, it is pushing the bonds down. And in a bent, we just say that the bond is less than 109.5. Depending on the bent. So there's 2 different bents. There's one bent where there's 2 shared and 2 unshared. That's the most common. There's another bent where there's 2 shared and only 1 unshared. So it's just less than. It could be 107. It could be 108, but we're just going to say less than. That's all the AP is going to make you do. This one has 3 shared regions and none of these weird green things, none of the unshared off of the central atom. So 3, the prefix for 3 always is tri. So this is trigonal. If there are 3 shared and no unshared, then this is planar. So this one sort of is flat like a piece of paper. These are not. So these are going to take up 3-dimensional spaces. This one's sort of flat. This one's sort of flat. These 2 are not. And so trigonal planar is between these angles. The measurement is always going to be 120 degrees. This one has 1, 2, 3 shared off the central atom and 1 unshared region. And so again, it has 1, 2, 3, just like this one has 1, 2, 3. So this one is also trigonal, but it's not the same because this one has no unshared electron clouds. This one does. And so this is trigonal, and we call it pyramidal. Because if you look at it, this is sort of making like the base of the pyramid, and then this would be going up to the top to the pyramid. For a trigonal pyramidal, we say that the bond is 109.5. And then this last one, we have 1, 2, 3, 4 shared pairs off of that central atom. There are no unshared regions. The prefix for 4 in chemistry is tetra. So this is tetrahedral. And in a tetrahedral, the bonds are also 109.5. So this makes sense. If you understand anything about angles, this is 180. It makes sense. These two should make sense because this is about 120 degrees between each of them. These are a little trickier. Just stick that 109.5 in your brain. So 109.5 for trigonal, pyramidal, and tetrahedral, because in essence, they have sort of the same structures, just this one is an unshared, this one is shared. And then that makes this one be less than 109.5. They just use this as the indicator for those. Those are your 5 main VSEPR shapes. So now we're going to talk about bond hybridization. Again, in order to do this, you have to have drawn a Lewis structure. And then once you have the Lewis structure, you look at how many regions of bonding or electron domains they have. So how many regions of bonding off the central atom. And if there's 2 regions, then it's SP. You add the exponent. So 1 plus 1 would be 2. There's an understood 1 if there's no exponent. 3 domains off the central atom would be SP2 because, again, 2 plus 1 would give me 3. 4 domains off the central atom would be SP3 because 3 plus 1 would give me 4. So let's go back and do that with this one. So I have 2 bonding regions off of this. So if I only have 2 bonding regions, then that is going to be SP. 1 bonding region, 2 bonding region. And so because of that, your linear is an SP for bond hybridization. So what this is saying is, this is going back to our electron configuration. It's saying whenever elements bond, that their electron configuration, the outermost electron configuration for their valence electrons, overlap and combine. And so this bond hybridization is saying this is what's overlapping if we had a bond like this. This one has 1, 2, 3, 4 bonding regions. So in this one, it doesn't matter if they're shared or unshared. It's not like VSEPR in that regard. It just means, what are the domains? How many sections off of it? So if it has 4 bonding domains, then it is an SP3. So bent is going to be SP3. Again, add up the exponents. This has 2 bonding regions. 1 plus 1 gives me 2. This has 1, 2, 3, 4 bonding regions. 3 plus 1 gives me 4. This has 1, 2, 3 bonding regions. So this is going to be SP2 because 2 plus 1 gives me 3. This has 1, 2, 3, 4 bonding regions. So it's the same number of bonding regions as this one. So this is going to be SP3. And this has 1, 2, 3, 4 bonding regions. So it's also going to be SP3. Once you've drawn a Lewis structure, you can figure all these things out. They are all tied together. It is just looking at it from 2 different perspectives. One is looking from the perspective of angles and shapes. The other one is looking from the perspective of overlapping electron configuration orbitals. The last thing is bond polarity. So we have already talked about a bond being polar. This is now looking at a molecule being polar. We looked at electronegativity values a long time ago, and it comes back up again and again and again. So just as a review, for electronegativity, it is increase up, increase across. And so our elements up here in the top right have the most, bottom left have the least. We have to now decide, is a molecule going to be polar or not? So if a bond is polar, then that's where we use these weird partial charge symbol to show that it was closer to one element than the other. we are going to be drawing in what is called a dipole moment, which is just an arrow to show the direction to which it is going to be pulled more closely for those valence electrons based on electronegativity. The arrow is going to point to the one that is more electronegative, which is where the electrons are going to spend more time. And so on these, you can label that partial positive, partial negative, but you don't have to. You do need to get in the habit of drawing the dipole moment vectors. So it's just a vector, which just means it's an arrow to show magnitude and direction. And all we're going to do is just show that direction for the uneven distribution of electrons. If a molecule has dipole moments that are not canceled out, it's a polar molecule. If they cancel out, it's nonpolar. I want you guys, when you're looking at these bond polarities, to think about the central atom, and if you are playing tug of war off the central atom, are things canceling as they are being pulled in? Are they canceling, or are they not canceling? So think about it. If you were in the middle of a tug of war and other things were pulling off of you, what's happening? So for these, we are going to do a lot of stuff. We are going to draw these structures. We are going to do the Lewis diagram. We're going to say the VSEPR shape. We're going to say the bond hybridization, and we're going to do the bond polarity. We're doing a lot with each of these. And so for these, we are going to go through and draw the structure for each of these. And then from there, we're going to label all that information. Okay, so for this first one, we're going to do HCl. So this has 7 valence electrons. This one only has 1. So I've got 8 total electrons I got to do something with. If you only have 2 elements, all they can do is bond to each other. Chlorine comes in with its 7. It shares 1 with hydrogen. Hydrogen comes in with its 1. So I've used 2, 4, 6, 8. And chlorine is stable. And remember, hydrogen is 1 and done. And that's all it can do. Okay. So now let's label VSEPR shape, bond hybridization, and then let's also do this bond polarity. So in this, if there are 2 elements bonded, the only thing they can be is linear. So this is an example of linear. It doesn't look the same as my linear I showed a minute ago, because the linear I showed a minute ago, remember, had 2 bonds. But if you only have 2 elements, all they can do is bond to each other, and they're only going to be able to be linear. If it is a linear bond, then we would also look at the dipole moment. For this one, we're not going to do the hybridization because it doesn't really, it has just sort of like an S, but they don't ever ask you stuff like that. So we're not going to do the hybridization for this one, but we are going to do the dipole moment. So if I think about increase up, increase across, then your hydrogen is less electronegative than your chlorine. So what happens here is we are going to draw our dipole moment arrow. And typically this is how chemists are going to draw it. They're going to draw an arrow and put a couple lines on the back to show, or 1 line on the back to show the direction and to show the magnitude. And so in this, it is going to point towards chlorine. Since it is pulling the electrons to chlorine and there's nothing over here to pull back, this is considered to be a polar molecule. Also, this bond is polar. So if this bond is polar, and that's the only bond there is, then it's also going to be a polar molecule. These elements are not sharing the electrons equally. So let's clear this one out and go to the next one. NH3. So in this one, I have 5 electrons from nitrogen, 3 from hydrogen, so it's 8 electrons again. Nitrogen is going to be my central atom, and the hydrogens are going to distribute off of them. This would be my skeleton structure. Nitrogen comes in with 5 electrons, 1, 2, 3, 4, 5, and so at that point it's stable, and I've used 2, 4, 6, 8 electrons, so I've used all my electrons. Let's do VSEPR shape first. For VSEPR, I have 1, 2, 3 shared, so I know it's trigonal. 1 unshared, so then we have to decide which one it is. So this one has 3 shared, no unshared. This one has 3 shared, 1 unshared, so it's trigonal pyramidal. It has 1, 2, 3, 4 bonding domains or bonding regions. This is unshared, but these 3 are shared. And so with that 4, it is going to make it be an sp3. And then we have to do our dipole moments. So again, if we think about our electronegativity, hydrogen is less electronegative. So what's happening is nitrogen is pulling all of the electrons from each of the hydrogens to itself. And so what's happening here is it is pulling those in. These are polar bonds, and there is an unequal pull to the center of this atom. So they are all pulling the electrons toward itself. These are all polar bonds, so this is going to be a polar molecule. Be sure you understand the difference between these two. So polar bond is meaning my bond between specifically nitrogen and hydrogen. That would be polar because they have a very large difference in electronegativity. Polar molecule has to do with these dipole moments. So nitrogen is pulling all 3 of those things into itself. There is nothing equal and fair happening there. It's being a big bully, and it's pulling all of those electrons to itself, and so it is also a polar molecule. CH4, carbon has 4 valence electrons. Each hydrogen has 1, so that is going to be 8 electrons. Carbon's going to be my central atom. The hydrogens are going to distribute around them. Carbon comes in with its 4 electrons and shares 1 electron each with the hydrogen, so I have 2, 4, 6, 8. Everything is stable. Now let's do VSEPR. I have 1, 2, 3, 4 shared pairs off the middle. So if we look back here, that is this one, 1, 2, 3, 4 shared pairs off the middle. And so this one is going to be tetrahedral. It has 1, 2, 3, 4 shared regions off the middle, has 4 electron domains, so it is sp3. And then we have to decide what's happening with our bonds. So the bond between C and H for AP Chem is considered to be a nonpolar bond. There's some discrepancy. Some people argue that it is nonpolar. We are going to say all year long that carbon to hydrogen is a nonpolar bond because that is what AP says. And that's what I'm testing you for, and that's what I'm preparing you for. So they are nonpolar. If you only have nonpolar bonds, then it must be a nonpolar molecule because if it's also a shape that is nonpolar. So in this, nothing is pulling. None of these are unfairly sharing the electrons, and it has 4 regions off of it. Tetrahedral is considered a nonpolar molecule because they're going to be pulling equally off of it if they were, but in this one it's a nonpolar bond, so it is going to be a nonpolar molecule. The shape is symmetrical, which is where the polarity comes from, and the bonds are nonpolar. CO2 is going to have 4 electrons from my 1 carbon, and then 6 for each of my oxygens. So I have 6 times 2, which is 12, plus 4, which gives me 16 electrons I got to do something with. Carbon's going to be my central atom. I'm going to put my oxygens on either side. The oxygens come in with their 6 electrons, and carbon has 2. This is going to be one where I'm going to take this one and make a double bond, this one and make a double bond because we don't want to have those lonely dots. So then I have 2, 4, 6, 8, 2, 4, 6, 8. So I've used my 16 and everything is happy. And so now we want to look at it and figure out what the shape is for each of for this molecule. So there are double bonds. They do not count as 2 bonds each. They are going to just be bonding regions. So this has 1, 2 bonding regions. So because of that, it has only 2 regions that are sharing, and there's no unshared off that central atom, so this is linear. It has 2 bonding domains, so it is sp. Now let's look at the polarity. If we are looking at the periodic table, carbon is to the left of oxygen, which means carbon is less electronegative. So in this, oxygen and oxygen are going to pull the electrons away from carbon. These are considered to be polar bonds. That's why I drew the dipole moment, because that only occurs for polar bonds. But it's like a tug of war. If I were standing in the middle and each of these were pulling with the same exact magnitude against me, I would not move. I am going to have an equal force pulling on either side of me. When that happens, it becomes a nonpolar molecule. Not all linear are nonpolar. This one is. This one, remember HCl that we did a minute ago, is not. And so you have to think about what's happening with the bonds, and is there a central atom by which it is pulling equally off of? Let's do our last example, H2O. So oxygen has 6, each hydrogen has 2, so I got a total of 8 electrons. Oxygen's going to be my central atom. And I end up with 2, 4, 6, 8, and everything is happy. I have 2 shared domains, 2 unshared domains. So for shapes, this one is bent. 2 shared, 2 unshared. But it has 1, 2, 3, 4 bonding or electron domains. So since it has 4, it is sp3. And now let's do our dipole moments. These are polar bonds. Hydrogen is less polar than oxygen. So what is happening is it is going to pull the electrons into oxygen. So there are polar bonds. They are not sharing equally. This is not a symmetrical shape. If we look back at the picture, it's got the 2 shared regions up here, and these 2 are pulling down here. It's not symmetrical like trigonal planar would be. And so this is also going to be a polar molecule. So all these go hand in hand, and we will practice these and make sure that we're comfortable with them, but they all go hand in hand, and they all start with this. You need to draw that Lewis diagram to figure out what's going on. Now, eventually, you might be able to look at the chemical formula and figure out all that stuff, but for right now, we're not ready for that. We need to draw this and have a visual to make all this information. Now, the one thing I did leave out on this one was the bond angles. Those are also going to be something we need to connect back to them. But for this one, I just wanted us to make those connections because I just introduced a lot of information to you all really quickly. So our last thing we're going to do is talk about a chart that sort of organizes all this information into one. So in these charts, an example of linear would be HCl. Most of them are going to be like CO2, where it has 2 bonding regions and no unshared regions, but HCl just bonds and it's just linear. They're going to be SP for the hybridization. I could have given that SP to the HCl, but it's a little bit weird and unusual. AP wouldn't ask a question about that. And polarity depends. It depends on if there are polar bonds and they're sharing equally or not. Bent is 2 shared regions, 2 unshared regions. Bond angle is always going to be that just less than 109.5. Hybridization is always sp3, and they're always polar because they're not a symmetrical shape. Trigonal planar is 3 shared, 0 unshared. Angles are always 120. It's sp2. They're always nonpolar because of that shape. Unless, like, there's some rare chances where you could have, instead of 3 of the same thing, you could have 2 of one thing and 1 of a different thing pulling off that central atom, and that makes this change. But for the most part, if we're looking just at the symmetrical shape, then it is nonpolar. Trigonal pyramidal is 3 shared, 1 unshared. It's going to be 109.5 for its angle. We just say less than 109.5 for bent, but it's 109.5 for trigonal pyramidal is what AP accepts. sp3, because there's 4 bonding domains, and it's always going to be polar because it's not a symmetrical shape. And then my last one, if I could get it to show it better, is tetrahedral. It has 4 regions, 0 unshared regions. It's 109.5 for its angles. It's sp3 because it has a total of 4. And it's always nonpolar, again, unless instead of like CH4, I had like CH3Cl. That would make it be a polar molecule because there would no longer be a equal sharing. That's the reason drawing those dipole moment arrows are so important to understand for this topic. So 2 more slides and we're done. It's a lot of information thrown at you. So the last thing is there are different types of names for bonds, depending on if it's a single or a multiple bond, and they are called sigma and pi bonds. Again, almost everything in chemistry is named based off of Greek alphabet, and so that's where this one comes in. So a sigma bond is a single bond, a pi bond is a double or a triple bond. All bonds are sigma, not all bonds are pi. And so a triple bond contains 1 sigma bond. I gave you the symbols for those 2, and 2 pi bonds. So when we're counting, we have to again start with a Lewis diagram, and then once we have our Lewis diagram, then we are going to go from there and count up all the bonds. And so in this one, I've got a couple examples. I have HCN. So nitrogen has 5 valence electrons, carbon has 4, hydrogen has 1, so that's 5, 9, 10 electrons I've got to do something with. If carbon is one of your options, it is going to be your central atom. Also, typically, if they give you a chemical formula, the way they give it to you is the order in which it's going to bond. So I'm going to put carbon in the middle, hydrogen over here, and nitrogen over here. I have 10 electrons. Hydrogen is 1 and done, so it's done. I've used 2, 4. If I want to do it the way that they come in, then I'm going to end up with this. Well, that's not going to work because nothing other than hydrogen is happy, so I've got to shift the electrons around. And so I'm going to take these, make a double bond, take these, make a triple bond. Okay, now that it's a little cleaned up, let's do our types of bonds. So this here, because it's a single bond, is a sigma bond. We'll say that this is a sigma bond because it's the first of these 3 bonds. So we'll say this is the single bond. Then we will say that these 2 down here are pi bonds. So this is a pi bond and that is a pi bond. So your questions will be worded in such a way it'll say how many sigma bonds does this bond have, how many pi bonds. It's just different things. So in this one, so again, all bonds are sigma. Everything is considered to have a single bond. We had to shift the electrons around to make this double and triple bond, so it had a single bond already. And so because of that, it has 2 sigma bonds, and then I have a double and a triple, so it has 2 pi bonds. Let's do this again with a different example. I have C2H2, so each carbon has 4 valence electrons, hydrogen has 1 each, so I have 4 times 2, which gives me 8, plus 2, which gives me 10. If you have carbon, you're going to put it into a chain if there's more than 1 carbon. So right now I've used 2, 4, 6, And we'd have those lonely electrons off of each carbon. That doesn't work, so I'm going to have to take these two. I'm going to have to take these two. Then we got to figure out which things are sigma and which things are pi. You do not have to label these. So for my sigma, all bonds are sigma. So this is 1. We'll say this is my single bond because that's the first one I drew. And this one. Single bonds are sigma bonds. And so I have 3 sigma bonds. Pi bonds are your multiple bonds. So I'm going to have 1, 2. So I have 3 sigma bonds and 2 pi bonds. Again, I have to draw the structure to be able to figure that part out. Our last slide is a lot of information. And a lot of this is stuff that AP says you need to know about, but they rarely test. So we will do stuff with this page, but it is unusual for us to run into things off of this page. First of all, AP will never test anything that has to do with, if I could get this to move, which I did, but not any better. Anyways, there it goes. AP will not test hybridization if it includes the d orbital. Those overlapping orbitals get more complicated. Remember that AP is just a basic understanding of chemistry. If you take further chemistries in college, you're going to run into some of these more complicated things. So I gave this to you, but you're never going to be tested. I just want you to understand where it's coming from. So for trigonal bipyramidal, these are all pretty much exceptions. These are all going to be the rare exceptions. Those first ones I showed you, the first 5, are going to be super common. These are rare. So remember we said phosphorus can have an expanded octet. And so if phosphorus bonds to 5 things and it has 5 bonding regions and 0 unshared pairs, then it is considered to be trigonal bipyramidal. Those bonds end up being weird, and there's some that are 120 and some that are 90. This is 5. So these numbers have to end up being 5. So I have 3 plus 1 plus 1, which gives me 5. Again, you're not going to be tested on this, but I do want to introduce it to you. Octahedral is if sulfur does its expanded octet and ends up bonding to 6 total chlorines. When it creates a shape, it creates an octahedral shape. Even though there's just 6 of them, it ends up with a weird shape 3-dimensionally. They are 6 bonding regions, 0 unshared. All of them end up with 90-degree angles, and it's sp3d2. Seesaw is unusual. This is where sulfur bonds to 4 chlorines. These are just examples. They could be different examples, but you're going to have 4 bonding regions, but you're also going to have an unshared pair. Because remember, sulfur can do its expanded octet. They're all 120 degrees. Square bipyramidal, I didn't fill in the information. I can't exactly remember. I think it has 5 bonding regions and maybe 1 or 2 unshared pairs. It's an unusual one. Square planar typically is going to be, if we see this as an example, it's going to be with xenon. Because remember, xenon can do an expanded octet, so it has 4 shared and 2 unshared. They're all 90 degrees. T-shape, chlorine is weird too. Phosphorus, sulfur, and chlorine can use that empty 3d orbital to shift their electrons around and make it have expanded octets. And so it can bond and ends up with 3 shared regions and 2 unshared. Some are 90, some are 180. And then this is another bent. This is the one that picture was showing a minute ago, but it's actually an exception. O3 is an example where you have 2 shared regions and 1 unshared region. In this bent, they end up being 120 degrees. It's just an exception to the rule. Again, with this page, it is rarely tested, and so I want to introduce it to you. We will occasionally run into this, but not very often. More likely that you're going to be asked just to draw a Lewis diagram of these and not actually have to do molecular geometry for these. So last question, and then we're all done with this topic. Which of the following statements is true that would support the claim of NO3 ion represented above to have 3 resonance structures? So remember, resonance is talking about how the electrons are being shared off the central atom. If there's more than one possible shape, then you would show how they're like it can have three different possibilities. And so in this one, let's go ahead and look at the bonding, talk about it. Remember, in resonance, these three bonds are all equal in length because we don't know which one it's going to do, because it could also do in double bond, single bond, single bond, or it could do in single bond, double bond. It's saying what are some claims. So if we look down here, it's talking about bond angles and polar species. So we need to look at this and figure out what its shape is and what its angles are. And so it has 1, 2, 3 shared regions off the central atom. That means that it is trigonal. It has no unshared, so it is trigonal planar. If it's trigonal planar, it has 1, 2, 3. It's going to be an sp2. And then trigonal planar is a symmetrical shape. And in all these angles, all these bond lengths are going to be equal. So since it's symmetrical, that means it is non-polar molecule. Nitrogen is going to be less electronegative. So my dipole moment arrows are all going to pull out. And remember, when we're doing this structure, it looks like one's pulling this way and two are pulling this way. So if I was standing there and that's how it was pulling, then I would pull this way. But since it's trigonal planar, it actually has those 120-degree angles. So all of them are pulling out, but they're pulling out equally. This is a symmetrical shape. And so this is not a polar molecule. So it says which one would support that, which of the following statements is true and would support it. So the oxygen to nitrogen bond angles are 90 degrees. That is not true, because since this is trigonal planar, they are 120 degrees. So that is not a true statement. One of the bonds in NO3 is longer than the other two. That is not true, because if it is talking about resonance, we said that all the bond angles are equal. So this first one, it is not a polar species. It is a non-polar molecule because they are pulling equal. We cannot be set on the fact that we think that everything pulls at 90-degree angles. They absolutely don't. It's actually not an angle for any of our things. So if we look back here, none of these are 90 degrees. We got 180, 109.5, 120, 109.5. We have no 90 degrees in this one. Now we have some freaky 90 degrees when we get to the weird shapes, but in our normal shapes, we just do not have 90 degrees. So even though we draw the Lewis diagram like it's 90 degrees, it's not. It's 120. They're going to pull equally and is going to be a non-polar molecule.